Welcome back. In these lectures, I want to say a bit about how connectionism came on the scene as a competitor to computationalism. An important part of that story is the development of artificial neural networks themselves. And so the story I'm going to tell about that is it's a commonly told story. It favors in some ways the artificial neural network tradition. It's a story of the underdog ultimately winning out in a competition. Um, so take that in mind because the the full careful historical story of what happened in all of in this history, I think remains to be told. This particular story is a bit of a story told by the victors, and is questionable just for that reason. But in 1959, as we've already studied a bit, Rosenblatt proposes this model of a perceptron. All of the perceptrons that, or almost all of the perceptron models that Rosenblatt considers, have certain features that make them simpler than artificial neural networks today. Two of those that are particularly noteworthy are that they have linear activation functions, or basically stepwise activation functions for individual neurons. What that means is that each neuron either fires or does not fire. There's no intermediate condition where it fires halfway, or that there's some kind of value between, say, 0 and 100 that is being passed along the network chain. So in that sense, they are discrete rather than continuous. They're on-off. These functions are sometimes called linear activation functions. Another major feature of the Rosenblatt perceptron, at least most of those that he considered, is that there was usually only one layer internal to the network. So they were relatively shallow in the terminology we would use today, rather than deep networks. They had very few layers, either one or two, but not more than that. And in the subsequent development of artificial neural network research, the problem that had to be solved before multi-layered networks really could be useful was there had to be a way to train the network so that the weights would be adjusted further back in this, in the multiple layers. Rosenblatt had a algorithm, or had a rule for how to train the network in repeated uses of the network, how to train it to become more accurate by adjusting the weights within one layer. But there wasn't the needed math to be able to basically adjust the weights throughout the whole network in a way that could improve performance. And that needed piece of math was what is sometimes called the backpropagation algorithm, or just backprop. And once that was on board, which was proposed in 1986, it had actually been discovered earlier, but it was shown to do what it needed to do in this important paper from 1986. After that coming on board, then it became possible to build networks with multiple inner layers, which allowed for a much more nuanced solution to, for instance, classification problems. So the combination of the continuous activation functions of individual neurons and the use of the backpropagation algorithm to train networks basically allowed for neural networks, conceptually, the development of neural networks that could solve a wider range of problems and could do so more successfully. So when those problems were solved, that actually answered the Minsky and Papert objections that were proposed at the end of the 60s. And that ended the first artificial neural network winter, as it's sometimes called. Sometimes it's called the AI winter, from the 70s into the early 80s. That thawed out the winter, so to speak, and then there was a efflorescence of different kinds of model architectures, exploration of ways to use artificial neural networks to solve different kinds of problems. And some of those are discussed in the Churchland article, but you can find more information about them in many places. And Sejnowski and Rosenberg's Net Talk is an example of that. But there were still limitations in using these networks, and one of the big limitations in performance, in hindsight, came from two sources. One, limited computing power. So in the 1980s, just raw computing power of the type that is discussed in or described in Moore's law was much less than it is today. It just was harder to run, longer, more energy intensive computations then than it is now. And at the same time, there was less data available. So as more and more information started to be, there started to be mechanisms for gathering information, for gathering data automatically and storing that information digitally. Then it became possible more and more to have the right kinds of data pools for training networks to become very adept at solving the particular problem that was posed to them. So if you think, for instance, if you know anything about ChatGPT, this contemporary large language model technology, you think about it for a bit. If you know a little bit about how it works, it's basically impossible without the internet, without an enormous repository of text that it can draw from and that it has learned from. And so, it's not until you have digitally accessible data like that you start being able to really take advantage of the architectures that have been around even since the 1980s. But again, lack of computing power to actually build and train such models, and lack of data to use to train such models prevented them from really being that useful. And so that middle period between the 1980s and the point at which, exactly when that is not certain, but the point at which the accumulated additional computing power and data made the application of these things, of these technologies, really impressive in terms of what they could do, is this sometimes called the second artificial neural network winter. And it certainly helped the case of the artificial neural network researchers that the dominant paradigm, which was the symbol processing approach, ran into a lot of problems, and that it overpromised. It promised more than it could deliver in the 1960s and 1970s. And so as people became part of what led to the greater interest in artificial neural networks was the frustration with the dominant alternative paradigm, which was the symbol processing approach. One of the remarkable features of artificial neural network research is just the variety of neural network architectures that have been explored. And so what I've included on this slide is basically a summary of many of the different, what you might think of as toggleable parameters of these networks. You can change how many nodes there are in each layer. You can change how many layers there are. You can set the activation function to a stepwise function or to something else. And incidentally, this is a screenshot from this really nice online playground for neural networks, where you can toggle a lot of these different features and then train a network and see how well it performs on different just sample data sets.